Okay, this is the Aspen tutorial for the Mean 421 project. We'll go ahead and run through a practice problem so that you can see how Aspen works, and we'll go through all the major steps. So the first thing that we'll do is we'll show how to start and set up Aspen. So that's going to be fairly easy. We can either access Aspen through coming to campus and using the application in 241G, or you can access it from your computer using apps.alter.town.edu. So that's the way that I'll access Aspen. So let me show you how I'm going to do that. So I've already logged into Aspen here. Or sorry, already logged into apps. So we can go ahead and click on apps. And there are different Aspen applications. We want to use the one that says Aspen plus V12. So you can ignore all the other applications. We'll use this one. So it takes some time to load up. So once it's loaded up, I'm going to show you how to change the unit systems so that you can use the units that you're most comfortable with. So I'm going to change the units to kilopascal instead of bar, or 8 atmosphere, or whatever the default units are. And we'll change all of the power and heat into kilowatts. So I already have something open, so let me show you what it looks like. What you'll have is you'll have a screen like this, and then you can go ahead and click on new simulation. So it should be opening up a new simulation for me. Okay, so this is a new simulation. And what you want to do first, as I mentioned, we want to change the units. So the way that we'll do that is we can go to unit sets and create a new unit set. So I will call this Omar. It's the unit sets that I like to use. And for mass flow, we typically use kilograms per second. Temperature, we typically use degrees Celsius, so we'll change that. And for pressure, we usually use kilopascals or megapascals, so I'll change that to kilopascals. For heat, we'll change this to the enthalpy flow to kilowatts, and the same thing with the heat. Heat, we can change that to kilojoule. And I think that's everything that we need to change. Let me just double check. Transport. Concentration. Okay, and if we go to concentration, we'll change energy to kilojoules, and then power to kilowatts, and work to kilojoules, so that everything is in nice units that we want. So then we can go ahead and change that to new units that we've created, the new units that we've created there. So now we can go ahead and introduce the problem. So this is the problem statement. This is from homework 3, question 5. So it says, consider a steam power plant that operates on the ideal regenerative Rankine cycle with a closed feed water heater as shown in the figure. The plant maintains the turbine inlets at 3000 kPa and 350 degrees Celsius and operates the condenser at 20 kPa. Steam is extracted at 1000 kPa to serve the closed feed water heater, which discharges into the condenser after being throttled to condenser pressure. Calculate the work produced by the turbine, the work consumed by the pump, and the heat supply in the boiler for this cycle per unit of boiler flow rates. So this is the schematic that is provided in the homework question. So what we're going to do is we're going to simulate this exact cycle. So we'll go through different steps in order to do that. The first step is to identify the component used in our cycle. So the component is the actual material that's flowing through our cycle. So depending on the different cycles, we have gas cycles, which usually use air. We have refrigeration cycles, which typically use some kind of refrigerant, and steam cycles, which typically use steam, okay, water. So you need to select the method used to determine the properties of your components. You can use the method assistant if you have trouble determining a good one. So let's show you guys how to do that. So we can go to setup and let's go to component lists. So under component lists, we need to specify the components. Actually, there's an easier way to go. We'll just go to properties. So properties here will list the components. So the component that we have in this case is steam. So if we type that out and press enter, we will get steam. You can do the same thing with maybe some other fluids. So air, maybe methane, refrigerants, R134A. So you can just type them up and enter, or you can use the find tool to find the component that you want. So we can delete these because we're only using steam for now. And then we'll select the method. So for the method, there's a list of methods that are used to calculate the enthalpies and the entropies. And these are called equations of states. So depending on what your application is, you want a different equation of states. So for example, if we go down to GRG 2008, it says it's a model for properties of natural gas systems. So if you're using something that has to do with natural gas, you might want to use this method. Whereas, for example, if we go down to, for example, this one, OLI, it's a property method for electrolytes applications. So it always depends on your applications. And in this case, for steam, we have multiple options that we can use that are specific for steam. So for example, we have here steam TA. So we have NBS and RC steam tables. This is another steam table. And then we also have, I think, one more somewhere, which was IAPWS steam tables. So the one that I'm going to use is a steam TA. And we can go ahead and start our simulation, or start working on our simulation. Whenever you see these blue check marks, that means that everything is complete and you can move on to the next step. So after identifying the properties, you can go to the simulation. So we go to our main flow sheet and we can start putting things into our flow sheet. So let's go ahead and go to our slides so that you have an understanding of what are we doing. So we'll use our schematic to determine which blocks are needed in our simulation. The blocks represent the different parts of a process. So we have a block for a heat exchanger, we have a block for a turbine, block for a condenser, block for a valve. So that's what the blocks are. So first of all, we need to put them into the simulation, and then we'll define what each block does accordingly. And that really depends on the application, but we will get to that. So if you look at our cycle, we'll start with heat addition removal. We have two components that do that. We have the boiler and we'll have the condenser. So this is where heat is coming in from outside of the cycle into the cycle. It's not a heat exchanger. We'll get to that in the next block. So to do this, we'll use something called a heater block. So to do that, we can go back to our simulation. Down here, this is where we'll find our blocks. So we have different categories: mixers, separators, exchangers, columns, reactors, pressure changers. Some of them are more relevant than others, but for any heat, we can find them here under exchangers. So as I mentioned, we will use a heater. So we can just click on it and then click into our sheet, and we will have our blocks. Whenever you have any blocks, you always want to rename the blocks so that you know what they're doing. So we can rename this one boiler, and we can also rename this condenser. Okay, and that's pretty much it for now. Let's go ahead and put in the other blocks. So we have a heat exchanger, which is the closed feed water heater, in which heat is being exchanged between one stream and the other. So we will use this heat X block. And it's in a similar location. It's under exchangers, heat X, and we just drag that in. And we can rename this to closed feed water heater. Okay. And that's what we want. We can go ahead to the next block, which is the throttling valve, which is located between stream 7 and stream 8. And it uses just what's called a valve. And a valve is a type of pressure changer, so it's going to be under here. You can see that's the valve. So we'll place it here. And I'll just name this valve. So we have turbines and compressors. So turbines and compressors are specifically for vapor or gases. So that's located between streams 4, 5, and 6. And of course, it's a power input, power output. So any compressor or turbine that uses some kind of vapor or gas, we're going to use the same block, which is this compressor block. We'll specify it to be a turbine a bit later, but that's what we will do. So we can pull in this compressor block to represent the turbine. But I just would like to make a note on the next slide that we have 2 turbines that will be used. So there's no way for Aspen to have a multi-stage turbine. So the only way to simulate it is to actually put in multiple turbines. And if you notice also that there's a split in the mass flow rate, one goes to another turbine and one goes to one goes to the condenser and one goes to the closed feed water heater. So we'll need something called a split. So let's go ahead and add our turbines first. So we have, I'll call this the high pressure turbine. And then we can put in another one called a low pressure turbine. Okay, so that's there. And then the next thing that we'll add is our splits. So in between, after the turbine, we have 2 streams. So we're splitting up one stream into 2. We will use something called a split block that looks like that. So let's go ahead and add that one. So it's under mixture splitters, and we have this. So after the high pressure turbine, we will have a split. We can call this split. And I don't really like the size of this, so I can make this smaller. Do something like that. Okay. So we have one last item to add, which is going to be the pump, in which it only uses liquids. So, which is located between stream 1 and 2. And it can either act as a pump or a turbine, similar to the compressor block. And it's represented by this pump. So we can go back to our simulation, go to pressure changes and go to pump. And we can place it in here and call it the pump. So we've placed all the blocks that we require for this simulation. The next step is to connect these blocks together. So we will use something called streams. So streams is how we will connect our blocks together to represent the order in which steps happen. We need to define at least one stream so that the simulation can be run. It is easiest to define the stream before the turbine because we know the temperatures and pressures. So what we'll do is we'll click on this material and we will just connect the blocks together. The red blocks represent required inputs. The blue are optional. So we have our first stream, which is connected to the turbine. And then the turbine goes to the split. I'll just rotate this icon to make things hopefully a bit easier. And then you can see that there's one output. One will go to the turbine, but we can always add the second one. And I believe this one goes to the closed feed water heater. I'd like to note for the closed feed water heater, we have two inputs. One is called hot, one is called cold. So the hot stream is the one that's carrying the heat, which will be cooled down. So the hot stream in this case would be the one coming from the turbine. So we can connect something like, we can connect it just like this. Okay. And what we can do just to make things easier, I will flip this one vertical to make the connection easy. And then we also have, after the turbine, it goes to the condenser. We can rotate this one. And then after the condenser, it goes to the pump. So let's rotate that one as well. And then from the pump into here, I'll go ahead and rotate that one, or flip it. And then out of the cold flow heater, so for the cold, it goes into the boiler. So I'm just doing this to make this nice and neat before we actually start the simulation. And then the output of the hot goes into the valve. And from the valve into condenser. So we'll just move this guy down here. We can move this out here. So the hot from the cold feed water heater goes to the valve, so that's correct. So something like this. And then from the boiler, we would typically connect this to the turbine, but Aspen doesn't really like closed cycles. So we'll just put the stream just like that. And as we mentioned, we need to define our stream. So we'll double click on this stream, and you can pick two parameters: temperature, vapor fraction, pressure, vapor fraction. You need two parameters to define the stream. So the stream is defined to be 350 degrees Celsius, and the pressure is 3000 kPa. And the mass flow rate, we'll set it to be 1. And the mass flow will be 1 kilogram per second. So we've defined one stream, and once we run the simulation, the rest of the streams will be defined. So we'll show you what happens, of course, at the end once everything's been defined. So here I'm just trying to make some room for organization purposes. Spit up. This a bit to the right. Okay, so similar to anything else, if everything is disorganized, you won't really be able to understand anything. So we'll try to space things out so that we can understand what's going on. So we've defined this, we've defined one stream, we've connected all the streams together, and we can go ahead and go back to our slides and set up our blocks. So we need to define what each block does. And there are multiple options for the different types of blocks, and it really depends on the specifics of your system. So we'll go ahead and go block by block. So we have one block, which is the boiler. So what does the boiler do? So the boiler heats up the stream to 350 degrees Celsius and 3000 kPa. And we need to tell it that. So what we'll do is we'll double click on the boiler in the simulation and specify that we know what the temperature will be after the block and what the pressure will be after the block. So let's go ahead and do that in our simulation. We'll double click on the boiler, specify the temperature to be 350, and specify the pressure to be 3000 kPa. So that's done, that's defined now. And you can see that there's a blue check mark. we go to the next block, which is the heat exchanger. We can also do the same thing for the condenser. So before we move on too far, we can do the same thing with the condenser. So the condenser, we can double click on that. And we know what the condenser does. It sets the flow to a vapor fraction of 0. And if you hover over pressure, if you specify a pressure, then it will go to that pressure. But if you specify 0, that's your pressure drop. So we have a pressure drop of 0 across the condenser. So that's it for the boiler and the condenser. So as we mentioned, you have to select the specifications according to the application. And for the boiler and the condenser, there was 2 different applications, and we selected them accordingly. For the heat exchanger, what the closed bead water heater does is it sets the vapor fraction for stream 7 to be 0. And it also sets T3 close to T7. But we'll take care of that a bit later because it really depends on one variable that we'll get to. So we double click on the closed feed water heater, and our specification is that the hot stream outlet goes to 0. So that's this stream S10. So the vapor fraction S10 would be equal to 0. So we can define that. So hot stream vapor fraction will be equal to 0. So we're done there. For the throttling valve, and we know the throttling valve just is an isentropic decrease in pressure. So it decreases the pressure to 20 kPa. So we need to specify that as our outlet pressure. Okay. For the turbine, we know it's an isentropic turbine, and the output pressure is 1000 kPa. So it could possibly contain liquid. So there's an option that we need to set accordingly. So as I mentioned, you can either pick a compressor or a turbine, but we'll pick a turbine, set it to be isentropic, and discharge pressure to be 1000 kPa. It's isentropic and 100% mechanical efficiency. This is just something to keep track of for the efficiencies. Always have a value so that it doesn't go to the default value. So let's go ahead and set up the turbine. We have 2 turbines, of course, and we'll set them up in the same way. So isentropic turbine, discharge pressure of 1000 kPa, 100% isentropic efficiency, 100% mechanical efficiency. Then we'll click on convergence. So you can see it sets to vapor only. But it's possible that we can have both vapor and liquid. So we can have a saturated mixture. So we want to specify vapor liquid. So that takes care of the high pressure turbine. We can do the same with the low pressure turbine. Okay. And the next one is the split. We really don't know how much the split is. So for now, we'll use any numbers. It's possible that we could get an error, but we will be able to manage it. We will show you in the end how to do that. So for the split, let me show you what we're going to do. We can specify a split fraction. So one of the streams would have 0.3 of the mass, and the other one would have 0.7 of the mass. So double click on the split. That's it. This is 0.3. And then the last one that we need to take care of is the pump. The pump is used to pump saturated liquid to 3000 kPa. And we just need to mention the discharge pressure and the same thing with the efficiencies. So let's do that. So we've defined all of the blocks. So once you've defined all of the blocks, you should be able to run the simulation. And you can see that everything is a blue check mark, so we're good to go. And the run button is up here. So if everything's as we want it to be, we can run the simulation and we should not have any errors. Okay, we have some errors, and that's just due to the cold feed water heater. And that's due to, we don't know what the split is, so it's possible that what's happening here is not really possible. So we might be asking for the hot stream to provide more energy than really possible. So what I'll do is I'll go ahead and change the split to some other number. So hopefully that we don't get any error, so that we can show you what the results look like. Let's try it one more time. Maybe we can try something 0.35. And here we can reset the simulation. So it goes to the very beginning, nothing is run. And then we can press run again. We're still getting errors, which is not a big deal. We can fix that. So the one thing that I want to show you is how to show your results or display results. But give me 1 minute to find a good split value, and we will continue the video. Okay, so I found a good value to use, which is 0.81, and you can see results are available. So we can have our results. So one thing that we want to see is, let's see our heat and work output. So for example, if we click here, heat and work, we can see how much heat and work is produced at each turbine, at each condenser, at each unit. So we can see the high pressure turbines, -24, 264 kilowatts. And it's negative because it's leaving the turbine. So anything that's leaving is negative, anything that's being added into is positive. So you can see that here at the boiler, and you can see that at the condenser, that Q out, and this is Q in. So just pay attention to the signs. We can do the same thing other than heat and work. We can see the temperatures at each stream. And we can also see the pressure. And if we want, we can also see the vapor fraction. It really depends on what information do you want to see on the flow sheet. So I think I'm happy with this. The only thing that we don't have yet is the split value. So like we mentioned, we said we would use any split value. So in order to find the correct split value, we'll use something called design specs in order to specify the split value based off of our constraints. So if you remember, the closed feed water heater, what we've said is that the output, let's go to the slide. So if we go to the slide with where we set up the block, here we said we will take care of this later at T3 is equal to T7, and we have reached that stage. So if you look, we want the outputs to be, let's just move this or this so that we can see this one. So we want the outputs of the closed feed water heater to be the same temperature. So you can see here 180 and 154 are not the same temperature. So we'll use design specs. So that's down here on the left under flow sheeting option, design specs. So we'll start a new study. So temp quality, we'll just call it anything that's just a name. And let's go ahead, and it's asking me what variables are you trying to study. So we have two variables that we're trying to study. We want to know what the temperature at we want temperature at S9, temperature at S10 to be equal. So we need those to be set as our variables. So let's go ahead and say T9. Okay. And we can go to the streams, stream variable. We'll select the stream variable because that's what it is. And we want stream 9, and we want the temperature. We can do the same thing for T10. So streams, stream variable, S10, and we want the temperature from that stream. So the specification, what are we trying to do? So what we're trying to do is we're trying to say, okay, T9 minus T10 should be equal. So T9 minus T10 is equal to 0. Or sorry, the expression would be T9 minus T10. We want that to be equal to 0. We'll put some tolerance so that it's possible to converge easily. And then it's asking us, okay, what do you want to vary? So we want to change the splits such that T9 and T10 are equal. So we'll go to the block variable because that's where we specified the split. So we will select the split, and the variable is fraction, and we want T3 or S3. It doesn't really matter because one of them is opposite of the other. So it's 1 minus 0.7 or 0.7. So we'll start with a lower bound of 0 and an upper bound of 1. And we can use a step size of 0.01. The step size really depends on what you're trying to study. So that completes the design spec study. So now if I restart the simulation and I press run, ideally the design spec study will take care of the equality for S9 and S10, and we'll see that those are equal. So what we can see here is that S9 and S10 have the same temperature of 180. And that's what we'd expect from the results. So I believe everything here is correct. And just give me a second to double check against the solution. And if everything is good, we're done here. I will show you also some additional ways of looking at the results on the streams. But let's just double check that these are good. Okay, I've compared the values for the results, so these are all correct. So that's why we ask you to do the hand calculation so that you know what you're comparing against and just not accepting things blindly from the simulation. And of course, there's multiple ways you can do the hand calculations. Maybe you might want to use another software, but we're asking you for hand calculations. But in industry, you'd probably use another software. So what we can do once we've gotten the results, we can look at the streams one by one or the blocks one by one. So for example, here we can right-click results and then see what's going on in that specific stream. So we know the temperature, we know the pressure, we know the liquid fraction, and we also know the mass flow. So what it turns out is that the mass flow for the split, we can see the results for the split. It's 0.75 and 0.24. So that's what provides the numbers. So we are done here. You can see the stream results. You can also see the block results. So you can see what's going on in each block additionally. And I think that's pretty much it for everything. If there's anything else that you need for this project, I will include I will make another video. But for now, I think this is good enough for you guys. If there's anything that you need from me, let me know and I will be sure to help. Thank you very much.